Welcome everybody. Today we're going to do an application of circular motion called orbital motion. Now the example that you have already been thinking about is for the Earth going around the sun. These are some quantities that I might find useful here. I'll let you look those up on your own. And in particular, since what I'm going to do to start here is treat the Earth as going around the sun in a perfect circle, undergoing uniform circular motion, I know that the angular speed is going to be equal to 2 pi, which is the number of radians in a full circle, divided by the period t. And then I can put this all together with facts that I know about uniform circular motion, which tell me that the centripetal acceleration that the Earth is experiencing needs to be equal to r, the radius, and this is the distance between the sun and the Earth, not the radius of the Earth or the radius of the sun, times that angular speed squared, which means I'm going to get r times 2 pi squared divided by capital T squared for the centripetal acceleration. Then I can ask myself, well, where does that acceleration come from? There must be a net force acting on the Earth. That force is entirely due to the gravitational interaction between the Earth and the sun. I happen to know that the gravitational interaction between those should be capital G, the gravitational constant, times the mass of the Earth times the mass of the sun divided by the distance between them squared. So I now have an expression for the gravitational force. That's going to be the same as the net force on the Earth because there's no other substantial forces here, which means that I can set that equal to the net force and therefore equal to the mass of the object, which here the Earth is the object that I'm considering, times the acceleration of the Earth, which happens to be this one that I found here. So I can then set this equal to, again, mass of the Earth comes along for the ride, 2 pi squared divided by t squared. So now I have this is equal to that. You can see that there's a little bit of nice canceling that can be done to get rid of the mass of the Earth. I think I lost a factor of r that didn't come along for the ride. We'll bring that on in here. And then I can solve this for whatever I want. In the activity, I had you solve for the mass of the sun. But what I'm going to solve for is to get all the radius on one side and all the periods on one side. So I'm going to move the t squared and the r squared off of here so I don't have any fractions. So what I'm going to get here is g times the mass of the sun times t squared is equal to, let's see, r squared, and r is r cubed. And then I'm going to take this 2 pi squared, and I'm also going to move it over here and write this like so. So now I have a relationship between the radius of the orbital motion and the period, the amount of time that it takes to complete that orbital motion. And the only other thing that matters here seems to be this quantity, which is capital G, which is just a constant, times the mass of the sun, and then 2 pi, which again are constants. So a couple of interesting things happened here. One is we didn't end up needing the mass of the Earth. It turns out that if you are undergoing orbital motion due to the gravitational force, that your own mass doesn't impact the period of motion. Only the mass of the object that you are orbiting matters. And of course, the radius. How far away are you from that object? So again, we derived this expression by thinking about uniform circular motion. We didn't actually care that it was the Earth going around the sun and not, for example, the moon going around the Earth or some other astronomical body. So this equation will work for any object that is orbiting another in uniform circular motion, as long as you put the mass of the object that's being orbited in here, and that object is much, much larger than the thing that is doing the orbiting. It turns out if you start relaxing the assumption that the Earth was moving in a circular orbit and you let it move in an elliptical orbit, you get an equation that is identical, with the exception that instead of the radius here, you have to replace this with a, which is the semi-major axis of that ellipse, but that it still gets cubed, and otherwise this equation doesn't end up changing at all.